in this section we're going to talk about limits. Okay, so first, what does the limit mean? Limits are all about the idea of what happens as we get closer and closer to something. Okay, or I always tell my students, if x gets really close to a specific value a, what does y get close to? Okay, that's the whole idea between the limit. Okay, so the official definition is the limit f of x as x approaches a. So we write a limit and we say x is going towards a. You notice a little arrow, so x is going towards a. If f of x is going to be, our y value will be called L. Or as x gets closer and closer to a, f of x gets closer and closer to L. Okay, so x gets really close to a, y gets really close to L. So as x gets really close to a, y gets really close to L, or our limit. So like if we wanted to find the limit f of x equals x squared minus 4 as x approaches 3, we say that's the limit as x approaches 3 of x squared minus 4. So what we want to see is x gets really close to 3, what does y get really close to? So by looking at our graph, we can see that as x gets really, really close to 3, here's my 3, I can kind of come from the left or I can come from the right, but I get really, really close to, it looks like, 5. So as x gets really close to 3, f of x gets closer and closer to 5. So that would be my limit. Or I could look at a table. So what you do from the table is you say you come from both directions. So coming from the left is you pick numbers that are less than 3 and you plug them in. So numbers less than 3, I could pick like 0 to 2.5, but I want to get really close to 3. So 2.9, 2.99, 2.99999. And notice my f of x values, when I plug it into my function, get closer and closer to 5. And if I wanted to come from the right, that means I plug in numbers bigger than 3. So I might start 5 and 4 and 3.5 and 3.2 and 3.001 and 3.001. And notice these numbers get closer and closer to 5. So you can do a graph, you can do a table, or you can just plug it in. So we can just plug in x equals 3 into f of x. So the limit as x approaches 3 of x squared minus 4 is you just plug the 3 in. So 3 squared minus 4 gives you 9. Sorry, it does not give you 9. What does it give you? It gives you 9 minus 4, which equals 5. So officially, our limit is 5. So that's what a limit is. As x gets really close to 3, y gets really close to 5. Again, 3 ways you can find it. A graph, a table, or just plug it in. So let's look at some more graphs. So you might have things that are kind of called piecewise functions, where you find your function in pieces. And when you're finding limits, it's important to know that it doesn't actually matter what's happening at your specific point, x equals a, just what happens really close to x equals a. So in these 3 graphs, notice here that we have our function is still defined at x equals 3. But here we have this hole at x equals 3. And so f of 3 is not actually defined. Or right here we have a hole, and they actually put in our point down below. So f of 3 is actually at a negative 2. But in all 3 of these graphs, notice that as we get really close to x equals 3, our y values get closer and closer to 3. So our limit is 3. Oh. It looks like my graph changed a little bit. Okay, so I had a 4, a 3, a 3. Okay, but remember, as you look at this, you're just saying, as x gets really close to 3, what does y get close to? Okay, and we're not actually saying what is y, we're just saying what does y get close to. And in all of these circumstances, here, y gets really close to 3. Y gets really close to 3. So your limit is 3, 3. This one happened before because I didn't draw the same exact function. And so we do have a limit even if you have a hole in your graph. So how do you define limits? So in our class, we deal with very simple functions. If you take a normal calculus class, it gets much trickier. But for our class, it's very simple. Okay? And if you look in your textbook, they have all of these limit theorems. You don't really have to look at those. Okay? All the limit laws are telling you that if you want to find the limit, just plug in a. As long as a is f of x is defined at that point. So this means really you can just plug in a as long as you aren't going to be dividing by 0, taking the square root of a negative, or dealing with a piecewise function. So again, as long as you're not going to get a mathematical error, just plug the value in, and that's how you find the limit. And usually in this class, we'll have issues because we're dividing by 0. So there's two tricks you can use to get rid of this. You can factor, or you can rationalize denominators. So let's see examples of that. So in this example, we want to find the limit as x approaches 2 of x squared minus 4 over x minus 2. If I just try to plug 2 in, I'd get 2 squared minus 4 over 2 minus 2, and that's, we don't care what it is on the top, we're dividing by 0, and that's a big no-no. Okay, so if you would actually graph it, you'd have a hole right here. Now calculators don't actually tell you this, they just kind of fill it in and tell you, oh, this is probably what they meant. But there is technically a hole at x equals 2 because you can't actually divide by 0. So what we'll do is we'll factor it before we plug in the 2. So x squared minus 4 factors to x minus 2 times x plus 2. And then those x minus 2's cancel, and we're just left with x plus 2. And you can plug 2 in now, so plug in a 2 for your x, and you get 2 plus 2 is 4. So that's your limit. Okay, so here's a few different examples. Find the limit as x approaches 0, sine of x squared over x squared. Notice, can I plug in a 0? No, because I'd have a 0 right here in the denominator. I'd be dividing by 0, so we can't do that. You don't actually know how to simplify this. You can't simplify sine of x. In fact, if you haven't taken a trig class, you don't even know what that is. Okay. And so we're not getting advanced enough in this class to use other tricks to find the limit, so we'll just look at a graph, which I just put it in my graphing calculator. And this is what it looks like. So we want the limit as x gets close to 0. So close to 0 looks like I'm coming up towards 1, coming up towards 1. It just looks like it's 1. So using the graph, we can see that the limit is 1. Okay. And using a table, I could pick numbers that are less than 0 and greater than 0, and numbers that are really, really close to 0, like these really, really small decimals. And notice it is undefined at 0 because I can't divide it by 0. But I seem to be getting closer and closer to 1. So as x gets close to 0, my y values get closer and closer to 1, which is why my limit is 1. Oh, and I forgot to say, after example 3, go look at example 4, part B, on page 85 to see how to rationalize with square roots. Okay, so we learned how to factor as a trick. There's another trick of rationalizing, and you can see that on page 85 in your textbook. Okay, just a few more examples of limits. Let's say we want to find the limit of cosine of pi over x. Again, if you don't know what cosine is, that's fine. Here's our actual graph so you can see what it looks like. Okay, notice we can't plug x equals 0 into that because we'd be dividing by 0. We can't simplify it. There's just absolutely no way to simplify it. Okay, and we don't know any other tricks. So we can look at a graph. Now, it's hard to zoom in because every time I zoom in, I just get something that looks like this. But it turns out that this function just oscillates. That just means it goes up and down, up and down, up and down, up and down. And no matter how much you zoom in, it keeps just jumping up and down, up and down, up and down. And the function never settles down. It just keeps bouncing between positive 1 and negative 1. And this means there's no limit because no matter how much I zoom in, I can't figure out what it is really close to 0. I could try and use a table. So I picked some x values, which probably seem arbitrary, but they're really not. It's just my understanding of trigonometry. And I can pick x from 1 down to numbers really, really close to 0. And notice my cosine values are at positive 1, or negative 1, positive 1, something close to 0, negative 1, positive 1, negative 1, really close to 1, really close to negative 1. So as x gets closer to 0, the cosine of pi over x doesn't get close to anything. It just keeps bouncing back and forth between negative 1 and 1. So again, this means there is no limit, and you say your limit does not exist. Okay. Here's an example of something closer to what you'll do on your homework. So here's a piecewise function. It's two different pieces. We want to use the graph to find the limit as x approaches 3. Well, as I come from the left, my limit seems to get closer to 1. But as I come from the right, my limit gets closer to 5. They don't agree. So because your limits from the left and right side don't match, we say that the limit does not exist. Because I can't decide if y is getting close to 1 or y is getting close to 5. So again, if they don't match, the limit does not exist. Okay, and just two more things here. What if you want the limit as x goes towards infinity? So this means x gets really, really big. What does y do? Lots of times you'll have this question if you have, say, like a horizontal asymptote. So as we look at this graph, we can just say, okay, well, as x goes towards infinity, what's y doing? Y goes to 2. So our limit as x approaches infinity of this function is just going to be 2. In this next one, we now want x to go towards negative infinity. So as x goes towards negative infinity, y is going to go towards, well, it seems like it's just going to keep getting bigger and bigger. It's just a basic parabola. Nothing's going to change. It keeps getting bigger and bigger. So y is going to go towards positive infinity. So the limit as x approaches negative infinity, or x gets really, really big negatively, it's negative infinity. So let's put the negative in there. Y gets closer and closer to positive infinity. And the very last thing you need to know is about limits and derivatives. Remember, in our last section, we talked about how we could use the difference quotient to find the derivative, and we had to say let h get really, really small. Well, letting h get really, really small, that's just the limit. Okay, so officially, f prime of x, we're not going to do anything new, we already did this in our last section, but it's just kind of more official now, is going to be the limit as h approaches 0 of your difference quotient, which is f of x plus h minus f of x all over h. So once again, we already learned the difference quotient, but we just said let h get really small. Well, now we can say it's the limit as h approaches 0. So if you take that limit, you get your actual derivative.